So we're very happy to have Jesse Taylor from MIT to tell us about hidden geometry of particle collisions.
Great.
Take it away.
Thanks for the invitation and pleasure to visit you all virtually. And hopefully at some point I'll get a chance to visit UC Davis again in person. And I'm going to be telling you about some work that originated actually in the world of artificial intelligence, though it's not going to be necessarily obvious from my talk that connection is there. So I'll try to highlight it a little bit. And in fact, my interest in the intersection of physics and artificial intelligence has grown over the past 3 or 4 years, so much so that I have a new hat that I'm wearing. The hat is director of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. So the NSF thought that AI was so important that they made us put it twice in the title. And you can see our logo looks like either a capital A with a lowercase I on top of it, so AI, or the letters F and I next to each other, fundamental interactions. And we're looking for interesting synergies between what's happening in the deep learning revolution, as well as what we think is going to be kind of the forefront of research in fundamental physics. So you can go to our website, ifi.org, to learn more about the things we're doing. And so behind the scenes, there's going to be artificial intelligence, though hopefully I'll tell you a story that's going to appeal to the theorist in us. And we're going to see that some of these ideas that are coming from the AI world actually have kind of deep relevance for fundamental physics. So the title of my talk is The Hidden Geometry of Particle Collisions. And maybe to explain that title, I should just remind you about the manifest geometry of single collisions. So we often look at beautiful event displays like this from the LHC. This is from the CMS experiment. We slam together protons. We see sprays of particles. And we're used to talking about the geometry of single collisions in terms of things like longitudinal boost invariance along the beam axis or azimuthal rotations around the beam axis. We're used to thinking about geometric data analysis strategies. So for example, I study a lot about jet clustering. So clustering is a generic geometric data analysis strategy. We can also talk about the topology. So the field of jet substructure is trying to quantify the pronginess of jets. And so this manifest geometry we're all familiar with, and this is not really what I'm talking about today. I'm going to be talking about a hidden geometry, something where we're going to have a geometry emerge from a different principle, and that emergent geometry is going to turn out to have some really interesting properties. So the hidden geometry of particle collisions, I can give you a little bit of a preview in the context of classic QCD event shapes. So you go back to the 1970s, work by various people, including my colleague Eddie Farhi, on trying to quantify how QCD-like or how jet-like collision events are. And so on the left-hand side, we have an event display from the Aleph experiment. And this is one electron-positron collision. And we see the manifest geometry of that shown in this event display. And what we're going to do is we're going to take that one event and we're going to summarize it as a single point in an abstract emergent geometry. And then once you have an emergent geometry, you can start to ask different types of questions than you normally would in particle physics. For example, you can talk about manifolds. And it turns out that some of the ideas going back to the early days of QCD are related to distances between events in this abstract space and manifolds in this abstract space. And a variety of collider data analysis strategies actually have a geometric meaning. Not a geometric meaning in the ordinary meaning of the collider geometry, but a geometric meaning in this emergent geometry that I'm going to be explaining today. So let me tell you who the people are who have been doing this work. So this work actually was carried out when I was on sabbatical. This is pre-COVID. This is me with my students, Eric Metodiev and Patrick Comiskey. So Eric recently received his PhD, and Patrick's on the job market right now looking for postdocs. And you can see us, on sabbatical, traveling around Geneva, going underground at the CMS experiment, having coffee in Evian, going to Montreux and going to the recording studio where Freddie Mercury and Queen recorded their last album. And then this traffic stop that we had on the north side of Lake Geneva, actually some of the ideas that I'm going to be talking about today happened there. So, when we used to all be able to get in person and travel around, it was always inspiring. And so in some sense, this is stories about what I ended up doing on my sabbatical, ended up discovering this new emergent geometry. So what I'm going to do in the rest of this talk is I'm going to just kind of walk you through as slowly as I can, just some basic facts about collider physics. What is a collider event? And this is where the kind of artificial intelligence world comes in. Because trying to answer that question, what is a collider event? Basically, you're asking, if I were to encode the data from a collider event and give it to a computer, what is the best representation of that information? So we'll have that. Then we're going to talk about when are events similar. And this is going to give us a notion of distance. And once you have a notion of distance, you can start to talk about geometry. And I'll spend the bulk of the talk telling you what are various things in collider physics and phenomenology that have a geometric interpretation. Okay, and since we're on Zoom and I can see posted size pictures of you, but interrupt me at any point, drop questions in the chat, and I'll try to answer them as I go. I want to make sure that you understand the basics of what I'm doing, because things are going to just keep layering on, and the level of difficulty will kind of ramp up monotonically. So please ask any questions that arise as they come up. And then just before I continue, there's someone in the waiting room. I assume I'm not responsible for admitting people from the waiting room. And John, you're muted if you're trying to tell me something.
Just ignore them. I admitted them and they have some problem joining. Don't worry about it.
Got it. Okay, great. Okay, so let's start off with the question, what is a collider event? So returning to this picture of an event display, and what we see is we see all the complications inherent in trying to reconstruct collision debris. But if you're just thinking about it at a fundamental level, what is the data that's contained in a single collider event? What it is just a collection of points in momentum space. So here I'm ignoring impact parameters. I'm ignoring the complications of trying to do particle identification. And I'm just saying the trajectories that are coming from the central collision point coming out, they have a px, a py, a pz, and an energy. And collections of points in momentum space, where that collection could be variable length. This is the fundamental data structure that we want to interpret when we are doing collider data analysis. And the reason why I bring this up is that this type of data set, a collection of points in momentum space, this has a name in the machine learning literature. This is known as a point cloud. And point clouds are ubiquitous in data analysis well beyond particle physics. So here's an example of a self-driving car with LiDAR point detection, where you have collections of points in X, Y, Z, and also time information. And a lot of the data analysis strategies that you would do in the machine learning context for, let's say, self-driving cars are relevant for what we do in collider data analysis. So for example, here you can see a segmentation task where you can identify interesting objects in this view. That corresponds in the particle physics context to trying to identify these collimated sprays of particles called jets. With jets, you'd like to tell something about the origin of those jets. So I've spent a lot of time thinking about telling the difference between a quark jet and a gluon jet or a boosted top quark jet. And that has an analog on the self-driving car context of trying to tell the difference between a bicycle, an automobile, and a pedestrian. So a lot of the data analysis strategies are similar. And so we can learn something from this literature in order to say whether something that's done with self-driving cars, whether that's relevant at all for particle physics data analysis. But there's a key difference between the data set of self-driving cars and the data set of collider data. And the key difference is that we know a lot about the process via which particle collisions give rise to collision debris. And we can use that knowledge to figure out what is the best representation of the information, in particular, the representation of that information that we have the most theoretical control over. So just reminding you about the way that jets are formed in QCD. So at short distances, we have proton-proton collisions. Protons are bags of quarks and gluons. So when I slam them together, I get quarks and gluons at short distances. They shower and radiate. Eventually, the strong force becomes strong. Hadronization kicks in. I have composite hadrons that eventually hit my detector. And if I'm thinking about this from a point cloud perspective, somehow I have to figure out how do I go from all the detections that are in my particle physics experiment and reverse engineer what was going on at short distances. And if I try to do this generically, it's a really hard problem. Understanding the dynamics of hadronization is difficult. Understanding the way that detectors work is difficult. But one of the things that we know from a theory side is that there's certain information that's robust, or at least more robust. That is information that we think we can calculate from first principles on partonic final states, on quark and gluon final states, and that there are good proxies for what you would measure if you measured it either on hadrons or on detection level. And that information from the theory side that's most robust is the flow of energy from the central collision point out to infinity. So this energy flow operator, it's a quantum mechanical operator built out of the stress energy tensor. So we have T mu nu, the zero component is energy, I is the flow, and the flow of energy from the collision point off to infinity. This is the information that's robust to hadronization and detector effects. This is information that collider physicists would say is infrared and collinear safe. This is information that's well defined for massless gauge theories. So unlike charge, where charge is difficult to define, or at least localized charge is difficult to define if you have massless fermions, here this is something that's perfectly fine if I have massless gauge theories. And this is something that's had a long history. People have been studying this, actually even earlier work in the 1970s, work by Katchoff in the 1990s, Hoffman and Maldacena kind of revised this in the conformal field theory context. And then there's been kind of a resurgence of interest on what can I understand by studying this energy flow operator. And one of the things you'll see is that studying this energy flow operator gives you an interesting way of doing collider data analysis that's different than some of the traditional things that we've done. So in a machine learning language, instead of dealing with point clouds, generic point clouds, when I'm focused on this energy flow, what I'm looking at is weighted point clouds. So I have directions, X, Y, and Z, and I'm going to treat energy as a linear weight. And I'm going to suppress unsafe, infrared and collinear unsafe information like charge and flavor. And I'm just going to focus on the flow of energy off to infinity. So you can think about this as what you would measure in an idealized calorimeter. So if I just take a square slice out of my detector and have a jet go into that square slice, what I'm talking about equivalently is an energy density. What's the density of energy on my detector cylinder? And the fact that it's linearly weighted in energy, that's the key thing for having a weighted point cloud. And the difference between a theorist view and an experimentalist view is that an experimentalist would say you had finite calorimeter segmentation, but a theorist would say I have, in principle, infinite angular resolution on this energy density. And I want to do all my data analysis strategies, I want to do all of them on this energy density information. And this is the starting point. So the answer to the question, what is a collider event? For the purposes of this talk, it's an idealized calorimeter energy density. And again, we came to this by thinking about how to teach a computer how to do various machine learning tasks. There's also some interesting QCD relevance of this in the backup slides. But this is the starting point. And from this starting point, basically everything else flows. So let me just pause here to see if there's any questions about this particular representation of collider data.
So you're working on a sphere or a cylinder or?
Yeah, so depending on what type of detector I have, I'd have different geometry. So here, these slides were made for an audience that doesn't know about transverse momenta. So I did everything in terms of cylindrical coordinates to make it a little bit easier. But for the LHC, it would be, energies would be measured in transverse momenta, and the directions would be done in the rapidity azimuth plane. So I'm imagining a detector cylinder for most of the plots that I'm going to be showing. But I'm using the language of energy flow just to just to minimize the number of subscripts.
And you don't care what type of particle is it, a muon, or you just add all of them together?
That's correct. I do not care about flavor and charge. It's kind of interesting. There's actually a way of incorporating mass into this picture. So there actually is a way of talking about mass flow. And that's work that I did in 2012, actually, for a completely different project, is thinking about mass effects. But for the purpose of this talk, think about everything as being massless particles, everything going at the speed of light, no flavor and charge information. So it's not the full information about a collision event, but it's going to be an interesting subset of information which will take us into an interesting direction. Okay. So now that I have this representation of collider events as being a kind of idealized energy density in a calorimeter, now you can ask a question that we don't usually ask in particle physics, which is, when are events similar? So what we typically do in particle physics is we take that energy flow, we compute some observable on that energy flow, and we fill a histogram one by one. So one event gives me one histogram entry, and that's the standard way that we do collider data analysis. when you're talking about when are events similar, you're imagining having a collection of events.
You dropped out.
And now you shift between the machine frame. So here are two collider events. Oh, sorry, I dropped out. Am I back?
You're back.
I'm back. Okay, so I'm not sure what part of this dropped out. So let me just say it again. So event similarity is not something that we usually talk about in particle physics. We don't usually look at pairwise relationships between events. Typically what we do is we take single events, fill them in a histogram, and that's the way that we do particle data analysis. Here, I'm saying if I have n events, that I want to look at n choose 2 pairwise measures of similarity and somehow use that to analyze my collider data. And this is something that's very standard in the machine learning literature, and there's a variety of techniques based on similarity of data points, and we're going to leverage those lessons for a collider physics context. So here we have two collider events, so two collections of points in momentum space, and we want to quantify how close these events are to each other. So one's from the CMS experiment, one's from the Atlas experiment. So you might say, oh, they're 8.5 kilometers apart because they're on opposite sides of the LHC ring. But clearly that's not a very useful notion of distance. And a more useful notion of distance would be one that would say that these events are similar to each other. After all, they're both multi-jet events. They both have kind of similar patterns of the jet radiation patterns. Apart from the fact that Atlas and CMS have chosen different color schemes, you could imagine these as coming from the same ensemble. And both of these could be coming from some multi-jet final state. So we'd like to have some way of quantifying that these are similar. And based on what I said in the previous section, quantifying similarity of these events is, for the purposes of this talk, quantifying how similar they are in terms of their energy density. So what I want to do now is I want to show an animation that hopefully works on Zoom that shows how you can compare the similarity of two energy flows. So what I've done is I've isolated a square patch of my detector, and I have a red jet on the left-hand side and a blue jet on the right-hand side. These correspond to, again, kind of localized lumps of energy. And one way of quantifying the similarity of these energy flows is by saying, how hard would it be to rearrange the red jet into the blue jet? So hopefully this movie plays. So what we're going to do is we're going to distort. Oh, it's really, really choppy. Apologies for that. So let's see. Let me see if I can give you a, if I could just play this movie at the top in a different mode.
Jesse, one thing you could, if you turn your video off during playing the animation, turn it back on.
Great. So I've turned the video off. Let's see if that works to make the animation better. Okay, so let's see if this works better. No, it's still choppy. Okay, well, I'll go out of this mode and just play the movie in here. It seems to work a little bit better this way. So what you're doing is you're distorting the red configuration into the blue configuration, and you're solving what's known as an optimal transport problem. You're basically saying, what is the most efficient way to rearrange the red configuration into the blue one? So in the machine learning language, this is solving an optimal transport problem. In the computer vision application, this is known as the earth mover's distance, which kind of makes sense. You're the earth mover and you're moving piles of dirt, in this case, energy from one place to another. The mathematics literature would call this the one Wasserstein metric. And in this case, the red and the blue jets are 125.4 GeV apart. That's coincidentally close to the Higgs boson mass. That's just an accident. But that basically says how much energy, or PT, do I have to move from one place to the other in order to rearrange the red configuration to the blue one. So this notion of distance, as I said,
sorry.
Yeah.
Why doesn't it depend on how far you have to move it? The measure.
Oh, it does. It's energy times angle. So it's in GeV times radian, and then we're going to normalize out by the characteristic jet radius. So we're going to measure in units of the jet radius how much energy times distance you have to move it. Yeah. Okay, so this idea of the earth mover's distance turns out to have a long history going back to the 1700s. So a French mathematician, Monge, was studying the problem of moving dirt around literally. So apparently in French, there's two different words for a mound of dirt and then a trench where the dirt's going to go. So déblai is the mound of dirt and remblai is the kind of the trench where it's going to. And Monge was trying to calculate, given some amount of dirt and some place to move it, what is the optimal way of doing that? This was formalized by Wasserstein in the 1960s, and then it came into the computer graphics world in the 1980s, 1990s under the name of the Earth mover's distance. And you can imagine you have two images, and you want to know how similar those images are, and so you can imagine distorting the pixels of one image to make it look like the other image. It's work in the sense of stuff times distance. So if your data set looks like it has some kind of additive weight, in our case, the weight is going to be energy, and you have some notion of distance. So in our case, that's going to be the manifest geometry of like rapidity and azimuth. That gives you a ground distance. If you have a weight and a ground distance, then that allows you to define a distance between distributions as an optimal transport problem. And it's basically how much work you'd have to do to make the blue distribution look like the red distribution. This has nothing specifically to do with particle physics. It's just about how do you compare distributions in a robust way. But we can import it into particle physics by making our weight energy, and that gives rise to this energy mover's distance. So on the left-hand side, you see that same two red and blue events before, but now with the black lines showing you the optimal transportation path for distorting the red jet configuration into the blue one. This optimal transport has units of GeV. There's two terms, one which is a cost to move energy, where you have to move all the energy from the red to the blue in a way where the amount of energy that you're moving is positive. And you need to make sure, again, all the energy is moved. So that's a moving cost. And then because in particle physics, we can have jets or events that have different energies, there's a penalty term associated with creating energy. And these two terms together give you a well-defined notion of distance, and a distance that satisfies an important property. It's a distance that satisfies the triangle inequality. And therefore, it defines a metric on the space of events. So by metric here, I don't mean what we talk about in GR. I don't mean like some kind of differentiable manifold, not that. A metric just meaning a notion of pairwise distances that satisfies the triangle inequality. The distances themselves are positive. They're symmetric. And I summarize all of the red radiation patterns into the single red star. The blue radiation pattern gets summarized to a single blue star. I now can talk about the distance between the red and the blue star. And if I had a third configuration, this green star, I can now build a triangle, and that triangle satisfies the triangle inequality.
Jesse, this is my
Yes.
That's the question, just to understand your definition.
Yeah.
So when the energies are different, I can't move, let's say the blue one has got more energy than the red one. Then if I'm trying to move the red into the blue, I sort of have to move all of the red, but I can't fill in all the blue. So I don't understand how you define the first term when you have differences of energy. That's basically my question.
Good. So you do it, you do in the cases where you have different amounts of energy, you do it in the cheapest way possible. So
so you create the new energy, for example, in faraway places where it's hard to get to, is for example.
That's correct. And far compared to what? Far compared to the jet radius R.
Yeah. Yeah.
So in the movie, unfortunately, it doesn't show smoothly enough. But if I showed this movie again, you'd actually see some of these dots that don't have lines connecting them. Those are ones that disappear under this.
Okay.
In many contexts, actually, what you end up doing is you just normalize all the energies to be the same, so that this penalty term is zero. So that's often something that's useful to do. But this asymmetric one turned out to be relevant for some of the things I'm going to be telling about, though I think I'm going to sweep a lot of that under the rug in my discussion.
Well, if you didn't have the second term, sorry if I can ask another question.
Yeah.
If you didn't have the second term, it's kind of obvious that the triangle inequality is true just because it's a minimum amount of energy, you know what I mean?
Yes.
Pretty obvious. But it's not at all obvious, at least at first sight to me, why, if you add the second term, it should satisfy a triangle inequality.
That's correct. And in general, it doesn't. So you have to choose this R parameter in a special way. And basically what you need to make sure is this R parameter is big enough such that it's never to your benefit to just destroy energy in a random place. You basically want to say that this term should be this term should dominate, and or rather, you should be trying to satisfy this criteria first, and then the residual, you work as hard as you can. The residual is soaked up by this. I agree. It's not at all obvious that this satisfies the triangle inequality, but it does. And in fact, it's known that it does in the computer graphics literature, where they use a similar version of this asymmetric transport plan there. And I don't have a good intuition for it, other than to say, you can think about this cost to create energy as if you put an extra particle off at infinity. So you put an extra particle off at infinity to balance the budget. And then the least thing that you want to do is transport energy to that point off at infinity. And it's strictly speaking not off at infinity, rather it's a distance r away from everyone. So it's like you have it's like you put this extra special point that's able to absorb things. And then you basically convert this problem into one that only has this first type of term.
Okay.
In fact, that's numerically how we actually do this calculation, is by adding a point off at infinity.
Yeah.
Or point at a distance r.
Okay. Thanks. That helps.
Yeah.
If two events look exactly the same except rotated from each other, now naive I would say these two events are the same, but from this method, do you still get a non-zero distance?
Yeah. So if you take two events and all you do is rotate, then by this measure you would get something non-zero. But this has been thought of in the computer graphics context as well. So if you have an image with a cat in one corner and you move the cat to another corner, but otherwise it's the same, you would say that those images should be the same. And so in that context, what you do is what's called the tangent Earth mover's distance, where you first allow yourself to perform all possible isometries free of charge. And then you do all possible isometries and then just calculate the residual distance after doing isometries. So in particular, for this particular configuration, I've actually transported all the events to be centered at 0, 0 in rapidity azimuth to get rid of basically 2 dimensions of my emergent space. I could have also done a rotation, but we decided not to. But different applications, you might do a pre-processing, basically doing various isometries to try to make your configurations look more similar before calculating this distance. Said another way, you get to choose what you want identical to mean. And if you think it should be identical up to rotations, basically mod out by rotations, great. If you want it to be identical, if you want those to be dissimilar, which you may want to do, you can do that as well. Yeah. Okay. So, we talked to a reporter at MIT News about this, and she said, oh, it's like kind of like triangulating your social network. Basically, you find your pairwise distances between all your friends, and then you basically figure out like what is the geometry of your social network. So kind of like a graph theory problem. So here are just 3 example jets. Again, apologies that the video is not really showing. But actually, let me just do this again, since it seems to play better if I do it somehow in here. Yeah. And you're just seeing the transport from a 1-prong jet to a 2-prong jet in green to a 3-prong jet in blue, and then back to the 1-prong jet in red. Obviously, this satisfies the triangle inequality. For 3 events, I can show this on a plane. Obviously, once I have more than that, to try to triangulate the space, it's actually not at all obvious that your space should have any kind of integer number of dimensionality. And in fact, that's going to be one of the interesting things that we can do with this space is we can talk about the dimensionality of the space, and I'll say that in a moment. But before I do that, are there any just questions about the definition of what we're doing? Again, a very different thing to do to talk about pairwise distances. And at this point in the talk, it should not at all be obvious that this is useful. Okay, and it should be not at all obvious that this is connected in any way to what we talk about in quantum field theory and collider physics. This is just data analysis strategies taken from the machine learning world and imported into particle physics, and just asking the question, what can we do with it? Okay, so let me just tell you what you can do with it, just in terms of one example, which is computing dimensionality. So I have many more examples on the backup slides. So let's say you are trying to figure out the dimensionality of your data set, and all you have are pairwise distances between data points. Well, one way of defining dimensionality is basically asking, your number of neighbors, the people nearby, how does that grow as you change your kind of sphere of influence, or change your sphere of consideration? So if I'm living in a city, and if I think about the number of neighbors that I have as I go out a certain number of blocks, because we're mostly confined to 2 dimensions, my number of neighbors grows quadratically. And so if you invert the neighbor relation and extract the dimensionality, if you take a logarithmic derivative of the number of neighbors as a function of radius, that gives you the dimensionality of your space. So here's an example of a spiral where if I zoom in really close, I just see 1 point at a time. So I'm dimensionality 0. So this is like all of us in COVID times. If I'm looking at a radius of less than 6 feet, then everyone's just 0-dimensional spaces. As we zoom out further, we see here that things are more or less filling space in 2 dimensions. I zoom out further and then I realize, oh, actually it's confined to a line. And then I zoom out further again and I see that I'm, again, kind of filling out space. And if I zoomed out all the way, I would have dimensionality 0 again. So this is a notion of an intrinsic dimensionality that I can get if I just study how the average number of neighbors changes with distance. And we can do this for QCD. So here is a first principles calculation with my students, Patrick and Eric, of asking what is the dimensionality of a jet as a function of the scale at which I probe it. Okay, so I've taken a collection of jets in theory land. So I'm imagining computing all pairwise configurations of a collection of jets. I've taken jets at a fixed transverse momentum. So these are all jets at 400 GeV. And if I probe them at a scale around 400 GeV, strictly speaking, divided by 2, but if I probe it around a scale of 400 GeV, my dimensionality is 0. Why? Because at that scale, I'm basically probing a single quark or gluon. And if I've centered everything to be pointing in the same direction by using this tangent Earth mover's distance to put the rapidity and azimuth always at 0, 0, then I have 0 dimensionality for the quark that's made of the hard process. Then as a function of scale, if I go to longer distances, so smaller energies, we see that this dimensionality grows. So in dotted lines, you see a leading logarithmic calculation. In dashed lines, you see a Pythia 6 calculation. And the dimensionality, it grows. It depends on the strong coupling constant. It depends on whether you have a quark or a gluon at leading logarithmic order. And it has a logarithmic scaling. So this is like, if you want to think about like anomalous dimensions, this is like kind of like an anomalous dimension, only this is like at a dimension that a computer scientist would understand, this correlation dimension or intrinsic dimension. And it's saying that basically QCD indeed is scale dependent. And depending on what scale you probe it, you have different numbers of effective degrees of freedom. And the number of effective degrees of freedom scales with whether I have a quark or a gluon. Why? Because gluons radiate more, therefore I get more gluons coming out. Quark radiate less, therefore I have fewer gluons coming out. And roughly speaking, the dimensionality is on order 5 to 10, depending on exactly what the scale that you're probing your jet at is.
Jesse, sorry,
Yeah.
I think there's something basic I don't understand here. So, I understand this idea of the idea of distance. You explained that very well. But now, what exactly is the definition of this scale? How does the scale come into the distance?
The scale is the EMD. So I have a bunch of jets, and I now say I want to look at I want to look at what it looks like when I'm looking at my all things that are at 400 GeV apart. And what I see is that at 400 GeV, I can't radiate out energy outside my jet cone. So if I'm looking at 400 GeV, I'm basically seeing everything.
So these are the dots are 2 jet events, dijet events, yes.
This is an ensemble of single jet events. So I have an ensemble of jets. So one jet. I'm only looking at 1 jet per event. So I have 1 jet per event, and then I have, let's say, 30,000, just to pick a number, 30,000, and then I calculate 30,000, choose 2 distances, and then from that I use this logarithmic derivative to figure out what the dimensionality is. Okay. It's not at all obvious that there's a way of doing a first principles QCD calculation of it. So it turns out that at lowest order in perturbation theory, optimal transport turns out to be pretty easy to solve. Why? Because at lowest order in perturbation theory, all you have is basically comparing a Born diagram to a single real emission diagram. So it's actually not that hard to do the calculation at lowest order in perturbation theory, because that optimal transport is easy. Higher orders, it's much more difficult. But yeah, you compute this, and you get something that looks kind of familiar. Logarithmic scaling with energy, color factors alpha s, but it's for a quantity that's defined in this optimal transport way. Yeah.
All right. Are you going to comment on why the red line is the quark one is seemingly agreeing better with the Pythia than
I'm not going to. So I don't understand this behavior, to be honest. And this is Pythia 6, not the latest version, Pythia 8, and I'm not confident in what's going on here. Also, I'm not fully confident in my calculation. That is, our calculation doesn't have error bars on it, so I don't know to what extent I can really trust this result. And in particular, this calculation is missing important, you might call them threshold effects, where actually understanding exactly what scale you're at. So it's not PT, it's strictly speaking PT over 2. So that's missing here, and you can't see that in leading logarithmic calculation. So it may be that actually the uncertainties are large enough to cover that, and this is something that we're trying to understand right now. What I can do is I can go to data. So looking at public data from the CMS experiment, you can ask whether that data agrees with simulated data. And so I'm wearing another hat. I've been an advocate for public data access in collider physics. And so what you see here is a mixture of quark and gluon jets. The black is public data from the CMS experiment. The orange is a simulation based on Pythia 6. And you see that these things line up really nicely. You also see that detector effects tend to increase dimensionality, which is kind of an interesting fact. But based on this, I would say we have some confidence that what Pythia 6 is probably correct. And the mismatch with the leading logarithmic calculation may correspond to some effect that we're not properly accounting for. But this is something that we're exploring right now. Okay, so there's a lot more that I can say about ways of using this from a data science perspective. So when are events similar? They're similar when they have small energy movers distance apart. And you could say, well, why this distance? Of all the distances you could have chosen, why did you choose this one? And prior to this research that I'm going to be telling you about in a moment, it was just, well, this is what we learned from the machine learning literature, and it works. So what's the problem? But the problem is, like, we'd like to understand at a more fundamental level where these things are coming from. And so now the next part of my talk about what can be geometrized, it turns out that if you geometrize using that particular measure, a variety of nice things happen when you come to thinking about quantum field theory and collider physics. So let me just pause for a moment and just see if there's any further questions before we move on. Okay, so what can be geometrized? So what are candidates for things to be geometrized? So, when I give summer school lectures about collider physics, I always show this master formula. Everything we do in collider phenomenology at some level is trying to measure or compute a cross-section. From a theory perspective, how do you get a cross-section? You get a cross-section by doing an integral over phase space of some amplitude squared. And then you always have to choose what you're measuring. So you have to choose an observable. And that observable is a function of your phase space point. And so what's kind of remarkable to me is that the notion of phase space and the notion of at least some class of observables have a very natural translation into this geometric picture. And so that gives us some enthusiasm that this might be a useful paradigm to carry forward. When it comes to thinking about scattering amplitudes or thinking about cross sections, it's not so clear. So I can't claim that I know exactly what that map is, but I'll give you at least some hints about where they might come from and how they might be relevant. But the hope is that actually a lot of things, in fact, this whole formula might be able to be translated into a geometric language. And if that would be successful, that would give you a different notion of what to calculate instead of scattering amplitudes, which is kind of a provocative thing to say. But I'll try to give you some evidence why that might be a useful thing to pursue. Okay, so let's start with phase space. So what replaces Lorentz invariant n-body phase space? Well, from the perspective of geometry, n-body phase space is just the set of all n-particle configurations. So again, all my events just become a single point. So this is, again, this Aleph event represented by a single point. And this is a multi-particle event. And so it is far away from the set of all one-particle configurations. What turns out to be interesting is that for Lorentz invariant n-body phase space, you tend to impose energy momentum conservation. And it turns out in this space is actually more natural to not impose energy momentum conservation, which I don't fully understand why that's the case. I'm not going to impose energy momentum conservation here. So I have these one particle configurations, and I can ask, how similar is this event to that one particle manifold? Well, not very similar. And I'll give a number to that in a moment. I can then say, the set of two particle configurations. But notice that because I'm talking about energy flow, if I take one of these particles and have it go to 0 energy, then it no longer contributes to the energy flow. So actually, this two particle manifold is a strict superset of the one particle manifold. Similarly, if I have two particles that are exactly collinear to each other, I then also go degenerate back down to the one particle manifold. But unlike Lorentz invariant n-body phase space, where going between 2 and 1 feels like a very kind of discontinuous thing, here it's actually just very smooth. You just move around in the space and you just ask, how close am I to the two particle or the one particle manifold? And you can do it in a smooth way. Similar, I can talk about 3 particle manifolds, and all these n particle manifolds are related to each other by taking soft and collinear limits. Okay, so this is what Lorentz invariant n-body phase space looks like. And in particular, there is no real distinction between whether I'm, have a particular multiplicity, but restricting to a particular multiplicity picks out an interesting manifold in this space. And I say the word manifold because it actually turns out to be a manifold in the mathematical sense that it's locally equivalent to Euclidean space. And in principle, I could do integrals over these manifolds.
Can I ask a question?
Yeah.
I mean, in the conventional sense, if I looked at all, I don't know, two particle events, for example, obviously Lorentz invariant phase space gives me a measure on that, right? But obviously that measure is not the same as the distance, the Earth mover's distance. But somehow it feels like there ought to be some relation, right? I mean, in the sense that, right? I mean, somehow Lorentz invariant phase space is the right sort of flat measure on n particle phase space. So can you comment on that?
Yeah, so this is what I need in order to bring this story to like the most satisfying conclusion, is if I could define integration on the EMD induced space. I know how to do integrals over each of these manifolds individually, but they're all sewn together in this smooth way, and I don't know how to do integrals in the full EMD induced space. But I can define balls in EMD space, and those balls in EMD space, I could use Lorentz invariant n-body phase space to kind of figure out an appropriate measure for it. But then kind of patching together all those balls is something that I don't know how to do at the moment. But that's where this would be. That's where this research program will be going. This research program will be going where you would have some meta notion of integration over a variable dimensionality that then, when you project to fixed n particle configuration, should give you Lorentz invariant n-body phase space.
But I guess, I mean, even if you have a volume measure, it doesn't give you a distance measure between points, right? So mathematically, there's no contradiction, right? It's actually an additional structure.
Let's see.
But is there some, what is the, I'm sorry, this is just maybe this is just a basic math question, right? If I tell you I have a space and it's got some volume measure on it, so I know how to integrate over something of it. And I tell you there's a distance measure. There's some way of computing the distance, some linear distance between points. Is there some compatibility condition?
Right. So the challenge here is that we have all this intuition from GR, where all of this follows from the G mu nu metric. So, and that's a space that has fixed dimensionality. And once you know what G mu nu is, you know how to do geodesics, you know how to do volume measures, you know how to do everything. So the problem here is that I don't have a good intuition for this space that has variable dimensionality, and I don't even know what it means to be volume, because it's a volume on a space that. So I can define balls, I can define regions, but I don't know how to define like the volume of that region. If I have a region that's close to an n particle manifold, then I can use that to figure out what the relevant local measure for an integration is, but I don't know how to sew those things together in a consistent way. So the one thing that so right now, this is just a statement about what the mapping is. The reason why I'm optimistic that this is the right mapping is for what I'm going to say on the next slide.
No, go ahead. I mean, I saw.
Yeah,
derail you.
Yeah, Yaroslav, yeah.
No, I had also a different question here on this, but maybe you can finish if you want.
Yeah. So what gives us meat to my mind is the following logic. So what the EMD does is it forces you to think very carefully about not only distances, but more specifically, when are things zero distance apart? So when are two events exactly the same? What does it mean to be identical? Well, things are identical if they have the same energy flow. said in the language of QCD, events are the same, or energy flows are the same if they're unchanged by infinitesimal and soft and collinear emissions. So when I have a zero energy emission, or if I have an exact collinear splitting, that means that that those two events are exactly the same. And what that means is that infrared divergences live together in this space. So instead of having a real emission and a virtual emission divergences living in their different Lorentz invariant n-body phase spaces, here they live on top of each other. So if I have some n particle final state and then I dress it up with a loop, then I have a virtual diagram that's living in n-body phase space, or sorry, living on the n particle manifold. Real emission phase space, which has the characteristic soft and collinear singularities of QCD, that real emission phase space has singularities when z goes to 0 or theta goes to 0. Normally, we would say, oh, I have a kind of a degenerate configuration or a divergent configuration rather. But here, when z and theta goes to 0, I'm going exactly onto the same place where the virtual emissions are living. That is, they're coexisting. The divergence here coexists with the divergence here. And I can be more precise about that. To be more precise, when I talk about an observable that's infrared and collinear safe, what I'm saying that it has a certain smoothness property that allows the real and the virtual divergences to cancel. And said in a geometric language, what I would say is that I have a notion of continuity. So infrared and collinear safety, which is, for the purpose of this talk, things that I can calculate in perturbative quantum field theory, those are, that is, observables that satisfies that property of being infrared and collinear safe, those are things that are continuous in the EMD space. That is, I can do an epsilon delta analysis where I can say I make a ball of size delta, and I know that my observable is always going to be close by this kind of epsilon delta type logic. And the reason why I put an asterisk here is because actually, if you study continuity, there's all sorts of different notions of continuity that people have. And those notions of continuity in this geometric picture turn out to map onto various definitions that people have given over the years for what infrared and collinear safety actually is. And the one that turns out to be, in some sense, the best one, turns out to be related to something that George Sturman worked on in the 1970s, but he didn't have a good language for it. And so now we can say that basically George's definition of infrared and collinear safety corresponds to what's known as Holder continuity in this EMD space. And so I have a notion of manifolds, I have a notion of continuity. I don't yet have a notion of integration, but it's starting to smell like this is the right way of talking about things, that various debates in the literature about what infrared and collinear safety actually means get resolved once you have a rigorous notion of continuity in this space. Yaroslav,
yeah, I had maybe it's irrelevant here, but yeah. Suppose that there is some, well, I can only formulate in terms of a theory, like nonlinear sigma model, when you have only even number of particles in any collision. So like odd numbers are not allowed. In the QCD, of course, this is not happening, but I just wonder if it causes any like, is there any modification to your setup if you can only jump by 2, but not by 1?
So this notion of distance is well defined, no matter what theory you're talking about. It's a question about whether it's useful or not. The reason why this particular notion of distance is useful for QCD is because it forces infrared and collinear divergences to be coexisting at the same point. In the case of a nonlinear sigma model, you can ask, what things do I want to put together? That is, what configurations do I want to be considered to be identical to each other? And if you can define what you want to be identical to mean, then you can build a space that has that as that distance measure. And it just happens to be that this particular notion of distance that we used is the right one if what you're trying to do is make sure that you respect the soft and collinear singularities of QCD.
Okay.
And other notions of distance, in particular ones that involve charge or flavor, don't satisfy that property. So in retrospect, one of the ways that you could justify why didn't we focus on charge and flavor, it's because we knew that in QCD, charge and flavor is not infrared and collinear safe. That's why I wanted to choose my notion of distance to be insensitive to that. But you can imagine trying to come up with new notions of distance that would put together at zero distance things that you want to be similar and push far apart things that you want to be dissimilar. And you as the user get to define what notion of distance is most useful for your application.
Mm-hmm. Okay, thank you.
Yeah, so based on this, I would say that the EMD seems to define the natural geometry for massless gauge theories in the sense of respecting the singularity structure of gauge theories. but I have no idea what it means to have an amplitude in this space. Amplitudes have fixed multiplicity. This energy flow does not have fixed multiplicity. So I've now given you a space, and somehow I want to talk about the probability of occupying that particular space. And if I knew what would replace amplitudes in this, that is getting rid of this notion of fixed multiplicity, then we'd really be doing something. So at the moment, this is a very open question about whether we could actually do calculations directly in this EMD-induced space. And assuming we can, that should, in principle, make actually calculations easier because, again, real and virtual divergences are coexisting kind of by construction.
Can I just ask a question about this? I mean,
Yeah.
there have been people that have been trying to define modified amplitudes so that the amplitudes themselves are IR safe, right? So that seems like that's would be the right, maybe the right direction for this, right? If somehow you could associate each of those points in your space with some appropriately defined quantum, you know, state,
yeah.
right?
Well, no. So, and this is the key thing, is that the energy flow is not a quantum state. That is, I can have multiple different non-interfering quantum states that have the same energy flow pattern. That is, if I have a ball of gluons coming out and a ball of quarks coming out, those have the same energy flow, but obviously they're non-interfering and they're not the same quantum state. So really what I'm talking about is I'm talking about not quantum states, but talking about density matrices. So another way of saying this is that the EMD seems to suggest that instead of talking about S matrix elements that connect, you know, Fock space to Fock space, we should be talking about somehow doing a density matrix type of analysis. So the people that I know who are trying to come up with new definitions of the S matrix, they're still thinking about it as being an amplitude, where you still have some notion of what quantum states you're doing. Here, it's not quantum states or not single quantum states. It somehow wants to be in a density matrix formulation, which is in some sense how you're going to get around this fixed multiplicity. That with density matrices, somehow it's very natural to talk about multiple multiplicities kind of coexisting. That also might suggest why this effort might end up hitting a dead end, that it's not somehow intrinsically quantum anymore, because it's based on the density matrix. And it may turn out that actually imperils any type of calculation done with this strategy.
Is the problem simpler if you send n to infinity, or does that make any sense here?
Good. So it's strictly speaking, it's an order of limits question, but yes, you can imagine doing amplitudes with n goes to infinity. And when n goes to infinity, then you've captured the whole space, and then you can just kind of walk your way down from n to n-1 and so on by taking various soft and collinear limits. So one possibility that we thought of is that maybe this actually suggests that you should be doing amplitudes in the n goes to infinity limit. And that amplitudes in the n goes to infinity limit, that's what's fundamental. And finite n is actually not so fundamental.
Yeah, that's kind of interesting, because from a very different perspective, this is what other things also suggest. There is some simplification for n goes to infinity in different contexts. But it's interesting that you see something similar here.
Yeah, there may be something related. Okay, so that's what I wanted to tell you about phase space. Let me now tell you about observables. And, there's a variety of collider observables that have been developed over the years. And remarkably, a number of them take the following form. So you take a single event, you have a set of events, and you take the distance of closest approach. So again, the EMD is a pairwise distance between different event configurations. A manifold is a set of events. So if you want to get from that pairwise distance down to something that depends on only a single event, well, just minimize over that manifold over that EMD. And this turns out to be quite useful. First, useful in understanding and maybe in a more intuitive way what was done in the 1970s. So if I look at thrust, this thing that I mentioned that my colleague Eddie Fari developed, and thrust tries to answer the question, how dijet-like is an event? Well, in event geometry language, you have an event, you have the manifold of all back-to-back two-particle configurations. For technical reasons, actually, it turns out to be back-to-back two-particle configurations that don't conserve energy, which is kind of interesting. And then you take that event and you find the distance of closest approach. That defines some observable. What does that observable have to do with thrust? well, thrust claims to quantify how dijet-like configurations are. This quantifies how close you are to the dijet manifold. And these are the same idea, just with some 1- signs and normalization factors. That is, the distance to the back-to-back 2-particle configuration, this is thrust up to, again, this slight reshuffling. Thrust is defined as a maximization problem over the thrust axis. Maybe not so surprising that a minimization over back-to-back 2-particle configurations should have the same form. But here's an old plot from Aleph. It's showing the thrust distribution. And if you take 1- this, then you would be computing this geometric quantity, namely the distance of closest approach to this manifold. What this allows you to do, though, is it allows you to now talk about things that don't have such a simple expression. And so with Carrie Cicerotti, who's a graduate student at Harvard, we developed an observable called event isotropy that quantifies how isotropic an event is. And the idea is just really straightforward. You take your event, you take an isotropic configuration, and you just say, what is the distance between your event and that isotropic configuration? This is a notion of isotropy that every other notion of isotropy will agree with this near the isotropic limit. Why? Because what do you mean by isotropic? You mean close to the isotropic configuration. And so every other measure of isotropy in some sense is bounded by this one. And you can use this to study various new physics scenarios beyond the standard model. And so Carrie actually just recently had a paper with Matt Strassler, Matt Reese, talking about how you could use this to understand certain hidden valley scenarios. And basically, what's really nice about this event isotropy is that it's extremely sensitive to deviations from event isotropy. So, for example, 10-body, 25-body, 50-body phase space actually look quite different by this measure, even though by more traditional measures, like thrust, you wouldn't be able to tell the difference as you change in multiplicity. Okay, so I'm running out of time. Let me just tell you a few more things, and then I can give you a whole separate story, maybe for people who want to stick around longer. So one of the things that we were hoping is that some work that I did on characterizing how the substructure of jets might be actually easier to understand in this geometric language. So n sub jettiness tells you how much is your jet configuration aligned with having n subjets. So tau3 basically says, to what extent does your radiation pattern look like it comes from 3 subjets? Tau2 is how much does it look like it comes from 2 subjets? And it has this ugly minimization, double minimization form. And when I was giving talks about this, I forget whether I spoke about this at UC Davis, but giving talks about this, people would say, "Oh, this formula, couldn't you come up with something nicer? Looks kind of ugly, might be difficult to compute. Maybe if you use this event geometry idea, you could come up with something that's cleaner, more intuitive." And it turns out that what you come up with is exactly the same. That is, n sub jettiness literally is the point to manifold energy movers distance. That tau3 is the distance between your jet and the 3-particle configuration. Tau2 is the distance between your jet and the 2-particle configuration. And this, in some sense, justifies why we wrote that ugly formula 10 years ago. And we did it because we were thinking about the singularity structure of gauge theories. The EMD properly respects those singularity structures. And it's maybe not so surprising in retrospect that you can cast n sub jettiness as this type of optimal transport problem. And it's not just n sub jettiness. Work that my colleagues did on n jettiness, which is used for n and LO subtractions. This also has a notion of distance of closest approach to a manifold. Certain jet algorithms have that form. In particular, sequential jet recombination schemes correspond to moving from the m particle to the m-1 to the m-2 to the m-3, and like seeing what those distances are and using that to define jet clustering. And even something like Pileup mitigation turns out to be related to this geometry. And roughly speaking, Pileup mitigation is when you have multiple proton-proton collisions per bunch crossing, you get uniform contamination. And so what you can do to remove that uniform contamination is start off with your contaminated event, find the uniform configuration, and then follow a geodesic away from the uniform configuration in order to get a cleaned up configuration. And that gives rise to kind of beautiful geometric drawings that I'm not going to explain just for interest of time. But this particular data analysis strategy also has a geometric meaning. And just more generally, 6 decades of collider physics, we've been able to translate into a new geometric language the notion of infrared and collinear safety, old event shapes, jet algorithms, jet substructure techniques, Pileup mitigation. And this has been a kind of remarkable to us to realize that all these ideas are really different facets of the same idea. And so now that we have this EMD paradigm, it'll be interesting to see what happens over the next 6 decades and see whether there's new things that we're able to do with this philosophy. Okay, so what can be geometrized? Infrared and collinear safety, observables, jet algorithms, Pileup mitigation, they all turn out to have a geometric representation. And I also told you about this event isotropy, which is a new observable that was inspired by this geometric picture. Okay, so my hour is up. I'm on slide 39 of 49. So we can pause here and give you the summary is that we were able to import techniques from artificial intelligence, image processing, import them into particle physics. It wasn't obvious that it would be useful. Turns out to be extremely useful and gives us a new way of thinking about our collider data. And then for people who want to stick around, I can answer the question of how far does this rabbit hole go? But let me pause here for questions. And for those of you who need to leave, that's no problem. So let me say the official seminar is over right now. And then for people who want to stay, I'm happy to tell you a little bit more.
Okay, let's unmute and clap for a very nice talk by Jesse. Just jump in if you want to. Let's have a little bit of a question period, okay, for a few minutes, and then if there's sort of questions about this part of the talk, and then people who want to stick around can stick around. So just jump right in. I don't want to try to do anything with chat, so just pipe up if you have.
One question is about this Pileup to remove Pileup. You say go away from this direction. Is that direction really well defined? You know where to go.
Yeah. So these what are they called? Stained glass windows, if you like. These correspond to different attempts to define going away. So Voronoi tessellation turns out to be a technique that tries to figure out what uniform is by tiling distance of closest approach or locations of closest approach and kind of subtracting uniformly from that. And this is an approximation to moving away from uniform. Something that's used in the heavy ion context is called constituent subtraction, and that's approximating going away from uniform. If you want to literally go away from uniform, there's a whole field devoted to kind of understanding essentially tilings of spaces, and a particular tiling called Apollonius tiling turns out to correspond to solving the problem of how do you optimally move away from uniform configurations. So this is one that's never been used experimentally. We're trying to do some studies on this and see whether it actually gets better performance by doing the strict moving away as opposed to these approximate strategies for kind of moving away from uniform. But yes, it is well defined. And I never thought that I'd write papers that had like theorem proof in it, but this is one of those things that we proved is that indeed this moving away is a well-defined EMD operation. Other questions?
Maybe a very naive question. Now you're working on the QCD like theory. What about general conformal field theory? You can using the energy flow to explore the correlation function, something like that.
Good. So in conformal field theories, there's of course Hoffman and Maldaceno's work on conformal collider physics, and people have been studying energy correlators in N=4 super Yang mills. And I don't know quite how to use this energy flow concept in that context yet, and what I might hope to learn, but I can tell you something that's semi-related. So this is work that's in progress, but I can show you what it looks like just to give you a sense. So if you go back to the 1970s, Bosch and Brown, Ellis and Love talked about this energy correlator, which is basically you take a jet, you take two of these energy flow operators, and you basically ask, as a function of the distance apart, how much is energy in one calorimeter cell correlated with having energy in another calorimeter cell. And you can do this for 2-point correlators, you can do it for 3, 4, and so on. And this is something that is totally well defined in conformal field theory, and in fact is the focus of Hoffman and Maldesena's paper. This has a long history in probing the collinear dynamics of QCD. And what's interesting is that the plots that were made back in the day didn't highlight one of what I think is the kind of coolest features of the extreme collinear limit. And we were able to actually study this same kind of 2-point correlation function with public collider data. And so this was in a single afternoon. Ian Molt was at MIT for the BOOST workshop, and he was trying to explain to me why energy correlation functions were so awesome. And at 2 o'clock, I said, I appreciate the provocative lunch. We should talk about what to do with it. And then 8 hours later, I sent an email back saying, oh, by the way, here's a preliminary plot that my student Patrick made. And so this tells you, well, probably tells you that more that Patrick's a very fast and reliable coder. But also what you see here is a plot that is just totally wild to me. So whereas every other study of this energy correlator was done in a linear scale, here if you go to log space, you can actually see this kind of flat behavior here is kind of representative of quasi-conformal behavior in QCD. So this is kind of what you'd expect from a conformal-esque theory, is a correlator that kind of has this roughly flat behavior where the differences in slope is kind of an interesting thing to try to compute. And then you see essentially a phase transition where the scaling dramatically changes to something that has slope 2 in this log space. And you just see a very clean separation between the partonic phase of QCD and the hadronic phase of QCD as measured by this 2-point correlator. So this 2-point correlator is just using the standard energy flow operator. This has nothing to do with the EMD, but it's somehow telling me that this energy flow picture is a useful picture for understanding the dynamics of quasi-conformal field theories. And in this case, you actually see this interesting phase transition behavior when the angular scale is basically like lambda QCD divided by the gen energy. And this is kind of just a fascinating way of probing the transition from the perturbative to the non-perturbative regime. Again, not specifically EMD related, but has the same DNA in that it's coming from this energy flow picture.
Okay, thanks.
What's happening on the right part of the plot?
On the right part here, that's when you actually run into the jet radius. So when you have 2-point correlations within a jet, at the jet radius, you can have the 2 points go outside the jet, and that's why you get a decrease in correlation. If I had a strict cone algorithm, this would be a more abrupt transition because I'm using anti-KT jets. It has a steep fall, but it's basically just saying I no longer trust this object once I've gotten outside of the jet radius. Other questions?
So if there aren't any more questions, here's what I'm going to propose. First of all, let's unmute and clap again for Jesse. Right.
Thank you.
And now I'm going to propose, anybody can object, but I'm going to propose that we give Jesse 10 more minutes. Okay, so that way people who stick around know that they're not sticking around for another hour and a half, okay, or whatever. It's going to be, we're going to give Jesse 10 minutes.
Yeah.
Hey, Nima would get another hour and a half. Why? Discrimination.
Well, I mean, if you want to, we can do this 10 minutes at a time. I'm trying to get you an audience, Jesse.
Thank you.
So,
thank you. I can definitely do it in 10 minutes. And
then if there are more questions about it, we can
then we keep going. And people should feel free to leave at any time. And by the way, I purposely spend a lot of time kind of slowly introducing the concepts, because in some sense the first part of my talk is more important if you want to explore this, and then we have long papers for you to read if you want to learn more.
Actually, for my part, I appreciate that. So
yeah.
Anyway, so anybody who wants to leave can go ahead and leave, but let's go for 10 minutes and then see where we are.
Okay.
Okay.
Okay. So how far down does this rabbit hole go? Let me tell you my whole talk again, rapid fire, okay? So we started off with the manifest geometry of collider data. And what do I mean by the manifest geometry? What I mean is that I have a direction space, a space of rapidity and azimuth. I have notions of direction in that space. I have an angular distance. This is the manifest geometry of collider data. if you want to write it down in 4-vector form and actually account for mass information, there turns out to be a nice way of generalizing this. But let's just stick with repeating the azimuth for right now. And what I said is you take directions, you weight them by their energy, and then what does that give you? That gives you an event. Okay, so what is an event? An event is just energy-weighted directions. And what I told you is that that event can be thought of now as a single point in abstract space. And I can use this optimal transport problem, this EMD, to compute the distance between pairs of events. And to answer the question, how far down does this rabbit hole does this go? It's basically asking, wait a second, can I just rinse and repeat here? Because now I have points, namely events, and I have a notion of distance. Could I just repeat the whole exercise again and weight those events and keep going down the chain? Okay, so what is it natural to weight events by? It's natural to weight events by their cross-section. So here I'm showing a bunch of events actually that their sizes are the same, because you can imagine this is like the events that's coming out of an unweighted Monte Carlo generator like Pythia. And so you have a bunch of events whose weights are given by basically the cross-section for making those events. And so now I have cross-section weighted events, and I can now summarize this into a single point. And this is what I would claim a theory is. So it's actually an interesting question about whether, so certainly if I give you a Lagrangian, then I can predict, at least in principle, the cross-section for any event configuration I want. So clearly a theory gives me a collection of events weighted by the cross-section. It's an interesting question, which I don't know the answer to, is whether given a cross-section weighted set of events, does that uniquely define the theory or not? Are there two theories that actually have the same flow of energy, but actually correspond to having some other properties different? And this is a question which I don't know the answer to, which I'd be interested to know the answer to. But in any case, I have this theory. I now say that theory is now a point in my space. And now I can compute not the energy mover's distance, but the cross-section mover's distance. So capital sigma delightfully looks a little bit like a capital E. And the cross-section mover's distance tells me how much cross-section times EMD do I have to move to make one theory look like another, okay? So you can imagine one dot here is the standard model of particle physics. Another dot here could be like the n equals 1 supersymmetric generalization of it, or I could have another dot being n equals 4 super Yang Mills. Like each one of those theories generates predictions for all the cross-section weighted events, basically predictions for all the energy flow patterns I could get. And using this cross-section mover's distance, I could do various things. So I have a distance between theories, and just like I had n jettiness, we use the EMD, I could talk about k eventiness, would compute the sigma MD. That is, I could talk about to what extent is a theory well described via kind of having k events. Okay, so it is not at all obvious that this notion of theory space is useful, but it's certainly something that I can define. And I can imagine even trying to, like, say I could have one theory be like QCD with one value of alpha s, and another theory being, you know, QCD if I change that value of alpha s. And this notion of theory space similarity might be useful for particle physics applications.
But you can only collide gravitons, or what?
Oh, good. So I actually haven't talked about the initial state. So this is one thing that I've kind of swept under the rug, is exactly what the initial state is. And what you just said, colliding gravitons, is the purest way of thinking about this problem. And one way of saying it is that if I were to collide gravitons and all I can measure is the flow of energy, could I reconstruct what that theory was? That's a fascinating question. For practical applications, I don't need to just talk about colliding gravitons. I can also talk about colliding protons and such. And then I just have to make sure that when I do this comparison, that I'm considering the same initial states. But yeah, the question of if I were to just do graviton scattering and measuring the energy flows, does that tell me everything about my theory or not? It's a fascinating question, which is either yes or no. And if it's yes, then that tells you something that, like, this EMD really is fundamental. If the answer is no, then the question is, what additional information do you need to specify a theory? And Is there some way of capturing like charge flow or something else? Like, what do you need to know about a theory? And this is kind of like the meta version of the scattering amplitudes picture, but now restricted to infrared and collinear safe information. And it may be that the answer is just that infrared and collinear safety is overly restrictive, and that there's other information that's not IRC safe that's necessary to define what a theory is. That's one possible answer to this question. Okay, so I said that this might be useful. Well, it turns out it's already been used. And this is kind of a surprise to me that this notion of theory space, a distance between theories, was already used. And it was used in a different jet physics context for jets that look like this. Okay, so here, this is not proton-proton collisions. This is lead-lead collisions, where you're making a droplet of quark-gluon plasma, and you have a jet flying out from it, but then another jet that's actually interacted with that plasma, and it gets quenched. That means it loses energy to that quark-gluon plasma. And it turns out that the notion of theory space is useful in trying to interpret this jet quenching data. Okay, so what are my two theories? So one theory is the theory of vacuum QCD. This is jet production with no medium. The other theory is in medium QCD. I'm making jets, but those jets have to fly through the quark-gluon plasma. And if I compute the cross-section mover's distance between one theory and the other theory, what I've done is I've found an optimal transportation plan that maps the jets that I see that have been modified by the QCD medium and mapping that to jets in vacuum. And this is a little bit of a holy grail for people who have been working in heavy ion collisions, because if you're trying to understand the properties of the plasma, you would like to know what is the property of the jet before it hit the plasma and then study how it was modified. Of course, we don't know how to do that, but here is an operational way of doing that. It's a way of defining a mapping, and you could hope that the jets that are mapped between each other give you some kind of useful proxy for thinking about how the jet was modified when it passed through the medium. And so in work that I did with Jasmine Brewer, Guillermo Milano, and then ongoing work with Andrew Turner that's somewhat related, we studied this jet quenching phenomena via a procedure that we call quantile matching. But the details of this procedure don't matter. All you need to know for the purposes of this is that this is equivalent to following a geodesic in theory space. So I have a cross section for all my lead-lead data. I have a cross section for all my PP data. I want to try to guess how much is the PP data modified when it goes into the lead-lead world. And if I do this transportation plan of moving this gray curve over to the black curve, that's equivalent to following a geodesic in theory space. And what this gives you is something that is a much more intuitive way of thinking about jet modification. So this is saying, if I do this mapping, when I go through the medium and I have a jet at a given PT, how much PT is lost by its interaction with the medium? And that's what this quantile QAA measures. And this is the contrast with what was typically done in the heavy ion literature, which is you compare things vertically. You say, fix the PT and ask, well, how is the cross-section different? But to the extent that you think that it's roughly the same jets being produced in vacuum in a medium, it's just that the medium jets have been modified, then this horizontal mapping is the more natural thing to do. And indeed, if you go to the machine learning literature and you ask, when is this cross-section mover, when is this Earth mover's distance used? It's used when you want to compare distributions horizontally as opposed to comparing them vertically. Traditional ways of doing measures like KL divergence, compare histograms vertically. The Earth mover's distance is special that it computes things horizontally. We use this in this work from last year. And remarkably to us, this turns out to be identical to solving this cross-section mover's distance problem. So that's what I wanted to tell you about in my 10 minutes. Here's the summary slide again. But it's kind of cool that you can start now like visualizing theory space as something and thinking about, what does it mean for theories to be similar? Here I define theories to be similar by this cross-section mover's distance. You can imagine alternate definitions of theory similarity that might be useful for other applications.
All right, cool.
So can't you use distance in theory space to quantify differences between machines? So two colliders each have a resolution distance in theory space, and I want the one that has the finest resolution, maybe.
Yeah. So more generally, what you're asking is you're saying, I have my measurements correspond to a point in theory space. Like that's the measured cross sections and event patterns that I have. And then I have the manifold of all possible configurations that I'm trying to distinguish. So if I want to say measure the top quark mass, I have a manifold of theories that vary only by me changing the top quark mass. And then the distance of closest approach would be the best fit top quark mass. And then you'd have some kind of smearing, experimental smearing that basically says that point is not really a point, it's really a fuzzy ball. And you want to see basically which one gives you the best measure, for example, for the top quark mass. Or for new physics scenarios, you want to say which one can distinguish better between different flavors of Susie, or which one would have reach for other types of phenomena. So yes, you could use this in that context. I haven't seen a killer app though where this way of talking about things actually leads to better answers than the way that we traditionally do things. That is, I don't yet see a case where I couldn't accomplish something with this concept that I couldn't do with another similar technique. In particular, standard hypothesis testing or standard uncertainty estimates seem to be perfectly fine for assessing differences of what collider you want to use. And I don't see that this is, at least at the moment, adding like something fundamentally new. What it does do is it gives me a new visualization strategy, which is helpful for thinking about what I'm trying to accomplish. And maybe one last thing to say about it is that computationally, trying to compute theory space distances is very computationally expensive, and it would be very expensive to try to carry out a full theory space analysis. So it may be that estimates or approximates to this theory space may be just as good for kind of practical applications.
I can also use it to figure out what my new theory direction should be. So I take the standard model and I take Technicolor and I say move in the opposite direction from Technicolor, because I know that's a bad direction.
So a really interesting question is whether movement in theory space corresponds at all to movement in Lagrangian space. So, we have an intuition for what theories like Technicolor look like. Is that intuition borne out such that tiny variations in Lagrangian space, do they correspond to tiny variations in the kind of event geometries that you get out? And it may be that this gives us just a new language to think about, like what am I trying to do when I'm looking for new physics? Am I trying to do parameter estimation, or what am I really trying to do is I'm trying to map out like all sorts of different energy flow patterns and making sure that I'm sensitive to them, such that I can kind of in a very model independent way say I am seeing configurations that the standard model doesn't generate, and it kind of points me in the theory space direction without me ever needing to say anything about a model or Lagrangian. I don't know if that's going to be useful, but it's something that you can at least dream up once you have this notion of theory space.
Well, we'd have to have
have a
access to
similar
the data.
question.
So say that again, John?
We'd have to have access to the data to do an energy flow analysis of all events.
Yeah, but with public collider data, we were able to do some of that. So I've shown you some public collider data plots where we've been able to.
You don't have run-2 data.
I don't have run-2 data, but it's a really interesting question for like thinking about how you would do an analysis. So I don't know how to do an analysis, but let me just show you something that's in that spirit. So let's say what I'm looking for is just weird stuff. Here's a histogram color-coded by weirdness. So I just have a collection of jets, and jets that have small values here have a small distance to the typical configuration. So you basically calculate the mean energy flow, and these have a small distance to the mean energy flow. And then going out further, you have exotic configurations, which are far away from the mean energy flow. And this is a type of histogram that you can make without ever having to say anything about a model or anything. You just say, look, just use this EMD, do an unsupervised learning strategy to try to say what configurations are anomalous, what configurations are typical. And this is the type of histogram that you're able to make using this. Now, the problem with this for the purposes of looking for new physics is that new physics may or may not show up as being so anomalous that it's in a way out on the tail. Like the Higgs boson does not have an anomalous energy flow pattern. It's just an overdensity someplace, and that would not show up in a plot like this. But if you're talking about like truly weird configurations, you can imagine trying to run this at the trigger level and trying to find what are the truly weird energy flow patterns and making sure that you store those to tape. That said, it's not obvious that weird energy flow patterns are where new physics would show up. But if that's where new physics would show up, a plot like this would show it. Yaroslav, you had a question?
I had a little bit related question. So, so suppose that you move in the Lagrangian space of theories and you find a point when there is a symmetry, which relays the coupling constant. So you would, from the Lagrangian point of view, it's kind of a preferred point. Yeah, there is something, let's say, in the S matrix, something about soft limits or something about properties. Now, in this, in your theory space, yeah, how would you, what would be special about that point? Yeah.
Good. So that's an excellent question. So you can ask from a collider phenomenology perspective, what's special about symmetries? And especially with this energy flow picture where I'm throwing out charge information, showing out flavor information, a lot of things that we often associate with symmetries, like internal symmetries, you just can't see at all. So like I'm blind to those in this representation. Nevertheless, you know, it could be that you have a beautiful structure that the energy flow could uniquely point to if you just knew how to interpret it. It's a little bit like if you're doing electron-proton scattering. So if you're doing electron-proton scattering, you know, you get some scattering amplitudes for electron-proton scattering. And if you analytically continue that, then secretly you have the whole hydrogen spectrum. The bound state hydrogen spectrum is lurking inside of the electron-proton scattering amplitude. But and as we know, the hydrogen atom has like beautiful symmetric structures if you think about it as a non-relativistic quantum mechanics problem. How would you know from electron-proton scattering that you have kind of the supersymmetric relationship that relates the hydrogen energy levels to each other? How would you realize that? And I don't know how you do it. Just like I don't know why we are confident that, like, if I measure enough S matrix elements, I can figure out what the underlying like theory is. Like, there's a long way to go from the things you might have experimental access to kind of what the intrinsic structure is. It would be very satisfying if somehow, if I had a symmetry that would correspond to something special in theory space, but it may be that there's nothing special. And the reason why it's nothing special is that energy flow is a very obscure way of capturing the information about a theory. On the other hand, I would have said before that S matrices are kind of an obscure way of capturing information about a theory, but of course we know that S matrix elements have enormous structure to them. And so it may be that once we understand what the amplitude analog of energy flow is, it might be that there you would start to understand that there actually are kind of interesting structures and that you might be able to lift that to theory space and so on and so forth. So, but at the moment, I don't see anything special when a theory becomes symmetric. One thing that would be special is if I move from a theory being in a confining phase to a deconfined phase, and there you expect the energy flow to be quite dissimilar as you move across that phase transition. So it may be that this is a better way of seeing kind of phase transitions between theories when they're in different phases, because there you do expect the energy flow to be quite dissimilar.
By the way, is there any kind of corner or any like simple toy model or example when you can actually study that analytically?
For theory space?
Yeah.
So the
analytic data.
Yeah. So the toy example that you can do is related to what I was showing here. So here we went to an extreme limit where we took. So if you remember, here I'll just I have the slide in front of me. 1 second. Okay. So we had this formula before. And we had two terms. We had a cost to create energy and a cost to move energy. If I take this R to infinity limit, this term goes away, and I'm just left with the cost to create energy. The cost to create energy is just, well, basically the differences of energy. And that's what we were able to study in this jet quenching example. So here it's just transverse momentum, or basically just modified energy. And so in that limit, everything becomes a one-dimensional problem, and we're able to do that analysis. So there are certain cases where you can map it to a 1D problem, and then it becomes very simple. The more general multidimensional problem, I don't know how to do in any analytic way. And indeed, while this calculation that I showed you before that had the computation in QCD of this intrinsic dimensionality, here I'm only able to get the answer to lowest order in alpha S. And once you go to second order in alpha S, I don't have a closed form expression for this. In fact, this I only have in closed form in leading logarithmic limit. So it would be awesome if there was a toy example for which I could do more studies of this. But right now, it seems very numerical. And prior to this most recent paper, I would have said it's all kind of numerical and that everything would be done with numerical analysis. And the fact that it happens to map onto all these other techniques that we're doing in collider physics, where we do have analytic tools for a lot of these, suggests that maybe if we just look through the right lens, we'll be able to kind of restore some of the analytic control that we're familiar with for traditional observables. So that was a roundabout way of not answering your question.
You exclude like charge and favor information because they are not inverse safe. Is there any way to include them, or? Yeah.
So let's just be clear that when I have massless fermions or massless matter particles, then charge and flavor doesn't make sense. So in particular, if I have QED, and if there's zero energy cost for popping an E plus E minus pair out of the vacuum, then I could have some event configuration that has charge going in some way, but then I could just easily just pop a zero energy E plus E minus pair out, and then my flow of energy has been modified. So when I have massless matter particles in the final state that carry charge, that's the reason why charge or flavor is not a well-defined concept. Once I have masses involved, then I can start talking about charge and flavor. And so what somehow you need to do is you need to somehow have a new notion of distance that for stuff traveling on the light cone, there can't be any charge information. But for stuff that's traveling subluminally, where you have mass, then you want to somehow insert charge and flavor information in there. And I don't know how to do that in a clean way yet. But that seems to be the next natural thing to do, is to say, how do you make charge flow information? How do you put that in a systematic way that knows to shut itself off when I go to when I go on the light cone?
Sorry, I mean, just a basic question though. I don't understand why charge and flavor is not well defined. I mean, by charge, I just mean abelian charge. So of course, color charge is a different beast, but like, because intuitively the E plus E minus pair, there's pretty much no cost to pop it out of the vacuum if it's collinear or very soft, but that's exactly when it doesn't matter. And more formally, you can define, just like you can define energy correlators, you can do that with any conserved charge.
Yep. And
so I don't understand your statement that for massless theories, you can't define flavor or charge.
So just to be clear, this is a localized notion of flavor and charge. And the asterisks that you'll run into when you study charge correlators, and so this is buried in the footnotes of people who study this when you're studying charge correlators, is that you find out that at a certain order in perturbation theory, you'll find out that it's not that it's no longer finite. So let me explain why this is the case. So if I take, so there's a soft limit where I have some process and I spit out a zero energy photon that has a soft singularity, and that zero energy photon can split to an E plus E minus pair. So that only has one singularity. It's only the soft limit of that photon, but it shows up at order alpha electromagnetic squared because I need to not only make that soft photon, but split it to an E plus E minus pair. That E plus E minus pair, because it's soft, it can go in any random direction. And so the flow just of charge by itself is soft sensitive. It's sensitive to this alpha S squared soft photon emitting basically a zero energy E plus E minus pair. So then you say, oh, but that's in the soft limit. So let's do energy times charge and study some kind of like product of J mu and T mu nu. Let's do that. But then if I'm studying energy times charge, then if I have a high energy electron that radiates off a collinear photon, I've decreased the amount of charge times energy carried by that electron.
Yeah, no, I got the point. Yeah. No, that makes sense.
So if you have a way of defining charge flow that's computable in massless gauge theories, I would be thrilled. And it's entirely possible that there is one, and I'm just not creative enough to see how to do it. But it does seem like charge and flavor is not something that's infrared and collinear safe, and therefore I don't know how to compute it perturbatively. That said, non-perturbatively, of course, is just an operator that I can study. And so it may be that if we take a more non-perturbative viewpoint, that maybe there's something else for us to do. But somehow, yes, somehow I would like to have a notion of almost like charge times mass. Like that's the thing that somehow should be meaningful, because when you have massive states, they can carry charge like electrons. We can count the number of electrons that go someplace because it costs a finite amount of energy to generate an E plus E minus pair out of the vacuum if you have a mass gap or if you have a gapped electron state. So somehow charge times mass, like that flow operator, must be the thing that you need to study. And maybe that's the thing that we should be studying correlators of. But I haven't been able to work out something that actually works thus far. It is late. The dogs are barking.
Sorry.
There's only 6 of us left. Anything else before we? Anything else before we adjourn?
Maybe. Well, do you have to go, Jesse?
I don't have to go immediately, but
Okay, well, anyway, I mean that's okay. That's fine. I had some even more like crazy, wild sort of questions.